Viewer, thanks for listening to my talk. Today I'll be telling you about some joint work with Khoury on a new version of the round elimination technique that can be used to show hardness results for distributed maximal matching. So let's set the scene. What are we talking about today? Today we are talking about the local model. So in distributed computing, there are many different models of computation. Today we're going to be talking about the local model, specifically the randomized local model, which is about message passing. So specifically, you have a graph and you have synchronous rounds where in each round you're allowed to send, each vertex is allowed to send a message to each of its neighbors. And the question is, after T rounds, you output the solution. And the question is, how many rounds of computation are required? How many rounds of message passing are required? This is a little bit complicated. A lot can happen in those messages, so it's a little bit more convenient to think about things as functions. So specifically, you can also think of an R-round algorithm as being a function that takes all of the information on all of the vertices in the R neighborhood of a vertex as context for outputting part of the solution. So this red vertex looks at everything in the 2 neighborhood, for instance, in a 2-round algorithm. And the question is, how small of a radius can we choose to make it so that we still get a solution to our problem, so that we still get an independent set or whatever we like. So that's the model of computation, message passing. And the problems we're interested in today are maximal matching and maximal independent set. And these are classic problems. Matching is a problem that I'm sure many of you have thought about matching yourself. Today we're going to talk about maximal matching, which is maybe a little bit less familiar to you. So because you're probably slightly more familiar with maximum matching, maximal matching is just a greedily or a greedily chosen matching. So a matching that you can't add to. So local optimum instead of global optimum. So we want to find a maximal matching or a maximal independent set. It's worth noting that maximal matching is easier than maximal independent set. Any algorithm is reducible to maximal independent set, specifically by taking the line graph. So specifically, you take your graph, your matching graph, you take the line graph, find an independent set, that's a matching in the original graph. And this shows that maximal matching on general graphs is no harder than maximal independent set on general graphs. And this is going to be important later. Okay. So we're interested in message passing for maximal matching and maximal independent set. What's known about these problems? Well, a lot is known. These problems have been studied for 40 years. So there's the classic algorithm by Luby and Alomba by Tai from 1986 that takes log n time for all of these problems. Just for context, the naive thing is greedy, which is highly sequential. It takes order n rounds. So Luby takes log n rounds, and there's been no improvement to this algorithm as a function of n in 40 years. This is an important context. We are unfortunately not going to be making that improvement today. We are going to be proving other results instead. So this was improved in the breakthrough work by Khoury, building off of Barenboim, Elkin, Petty, and Schneider, which shows that maximal independent set, and in particular matching and vertex cover, can be solved in log of max degree time. So log d time, where d is the max degree. This algorithm also can be shown to take square root log n rounds in trees via a reduction. And interestingly, Khoury and I improved this runtime for maximal independent set only. So this is so for matching, the state of the art is still square root log n, but for independent set, there is actually a better algorithm than square root log n rounds. It works for trees, and it also works for graphs with constant girth. Not in square root log n time, though, in log d divided by log of log star of d time. So this is all randomized algorithms. There's also a beautiful line of work on deterministic algorithms for maximal independence set that has culminated so far in a breakthrough work by Khoury and Grunau that takes log to the 5/3 n time. So that's on the upper bound side, algorithm side. On the lower bound side, we have roughly matching lower bounds for all of these problems, specifically up to like log n factors. But we don't have tight results. There are no tight results for these problems. And there's also, in parallel to all of this, there's also a lot of these lower bounds are for not necessarily regular graphs. For regular graphs, and also as a function, like for low degree graphs, there's actually a much stronger lower bound of order delta. This is due to the very nice work from FOCS 2019. Okay, so this is the landscape that we have so far on the left. So we have lower bounds somewhat close to upper bounds, but like not close enough to really understand the relative complexity of these problems. And that's what we're going to do. We're going to show a lower bound that'll much better understand the relative complexity of these problems. But before we talk about our lower bound, let's talk about the existing work. So in particular, lower bounds for distributed problems largely fall into two different categories by techniques. So the first is indistinguishability. And this is sort of a classic indistinguishability work is the work by Kuhn, Moscobroda, and Wattenhofer from 2004. So this showed a log d over log d square root log n over log n round lower bound against matching, or against vertex cover, which also applies for matching in MIS. And the idea here is indistinguishability. So you create a really weird graph that has two nice properties. First one is a local property that every vertex has the same R neighborhood view. So some symmetry up to distance R, or a lot of vertices, not necessarily all. And secondly, there's a global property, which is that if all of these vertices behave the same way, you get a vertex cover that is not a good approximation to optimum, which is a contradiction. So a distributed algorithm only has a local view, so therefore a bunch of vertices behave the same. But the fact that those vertices behave the same means that you get a huge vertex cover contradiction. So this shows hardness for maximal matching on irregular graphs. This graph crucially has a lot of vertices with different degrees. And it's worth noting that this is not improvable because of the fact that it applies to vertex cover. So the fact that it's a strong hardness result means that there's a matching algorithm by Ben Besat, Sensor-Hillel, and Schwartzman. So we have to show a direct hardness result for maximal matching if we want a better hardness result. And that's where round elimination comes in. Basically, this technique of indistinguishability, it's not taking advantage of the independence that edges are edge decisions have because of the fact that they don't completely have the same knowledge. So they showed several. There was this breakthrough work from 2019 that showed its order delta lower bound for maximal matching. And the idea is as follows. We assume that there's an R round algorithm for matching. This implies an R minus 1 round algorithm for another problem, which implies an R minus 2 round algorithm for another problem, etc., until you get down to a trivial problem or non-trivial problem that has a 0 round algorithm. But non-trivial algorithms are non-trivial, so they don't have a 0 round algorithm contradiction. Okay, so this shows hardness for regular trees, which is kind of a nice thing that the KMW result did not show. This is a more fine-grained technique than indistinguishability, and there's a long line of follow-up work that applies this technique to huge numbers of problems. But none of these papers broke through the log n barrier. So they applied it to they applied round elimination to many problems, but they were not optimally applied. So they don't necessarily always lead to optimal results. So in order to improve on KMW with round elimination, we need to break through this barrier. And that's what we're going to do today. So specifically, our main result is that there is no algorithm for matching better than log D, the minimum of log D and square root log M. And one major development that's happened since we've posted this paper online is that Baliu, Casagrande, Diamore, and Olivetti have simplified our result and extended it to some nice problems, coloring problems and other problems. So this is our main result, that maximal matching on regular trees requires the minimum of log D and square root log n rounds. Let's talk about why am I interested in this problem, for instance? So there are many reasons to be interested in this result. So sort of just the first one that comes to mind is quantitative. The big quantitative reason to be interested in this result is that this is the first improvement in the complexity of maximal matching and maximal independence set as a function of n in 20 years, because the previous state-of-the-art bound for these problems was square root log n over log n due to KMW. But this may or may not be tight because the best existing algorithm is Luby's algorithm as a function of n. But that's nice, but it's sort of, you could say, well, you're only improving that lower bound by log n. So what's the, or square root log n? So, we shaved a little bit off. What does that really mean? Well, one nice thing is that we do get some optimality results out of this. So in particular, we're showing that Khoury's algorithm from 2015 is optimal for MIS. And furthermore, that maximal matching on trees requires exactly square root log n time. So these are we're showing that for two separate problems, MIS on general graphs and maximal matching on trees, we have closed the complexity of those problems. These are not even there's a constant factor better. There is nothing better. So these problems are closed. But you could argue, well, the previous result almost closed the problems. There is only this log gap. So what's the conceptual message here? And I think for me, the coolest part of this result are the separations that this result shows. And these separations were not possible before our result. Because in order to show these separations, you need to have exact results, not results losing a log-log factor. And sort of the weirdest result is that maximal matching is actually strictly harder than MIS on trees. So this is a little bit funny because on general graphs, we learned that maximal matching is no harder or like effectively easier than MIS on general graphs. So maximal matching is easier than MIS on general graphs, thanks to the line graph reduction. But crucially, that reduction did not preserve being a tree. It, like taking the line graph takes a tree and turns it into a graph with a bunch of cliques. So what we're showing is that is not an accident. The complexity of these problems actually reverses on general graphs. This also, it's worth noting also that like this other result of ours is a crucial component of this. Like the better algorithm, like we found a better algorithm for MIS on trees than square root log n, and that's important for this. And then there's a trivial implication of this, which also is very interesting to notice, which is that MIS on trees is strictly easier than MIS on general graphs. And so this is one of the first cases of a separation between a problem on trees and a problem on general graphs, which is interesting because a lot of the hardness results in distributed computing are on trees. So we're starting to penetrate the terrain of hard instances for distributed problems that are not trees. And then lastly, there's also we also show that maximal matching on general graphs is strictly easier than vertex cover on general graphs. So there's always been this this triple of problems: vertex cover, maximal matching, and maximal independent set, where vertex cover is easier than matching, which is easier than MIS. We are showing that there is a separation between the first two problems. For a wide range of delta, this was also known to some extent for like very small delta. But we're showing it for a broad range of delta. And then technically speaking, the technical meat of our work, the key technical contribution is that we broke through this log n barrier for round elimination. Okay, so that's what we're doing today. Now I'll start talking about how the result actually works and how we prove the result. And the hard instance, so we're proving a hardness result. Let's talk about the hard graph. It's a random d-regular graph. It's been used many times before. The key properties of a random d-regular graph to keep in mind are, well, it's d-regular, and it has high girth, and with positive probability it has high girth. So in particular, locally, the view of every vertex is a d-regular tree. So like locally, every vertex in the graph has the same view. But globally, there is a no large maximal independent set. So in particular, that makes it so that it's globally not a tree because trees have large independent sets. Okay, so now we're going to talk about one key point of departure between our version of the round elimination technique and the existing approach. So in the existing round elimination framework, if you want to show a hardness result for your favorite distributed problem L, which you can sort of think about as what's called a locally checkable language, matching is such a problem because you can check that a matching is maximal in a local way, just one vertex at a time. So the idea is if you want to show a hardness result for your favorite problem, start by encoding as a language. Encode it in terms of the constraints that are required to be satisfied. And then once you have that, there is this machinery that takes this problem and turns it into another problem for which an R-1 round algorithm exists if an R round algorithm existed for the previous problem. But there is a big blow up that happens when you do this for randomized algorithms. And the way that we're going to avoid that is by not choosing to encode all of the constraints of the problem at once. So in particular for maximal matching, it's helpful to decouple the maximality from matching. So just consider algorithms that output a matching and assess whether they can produce a maximal matching, like how often they can produce a maximal matching. So in particular, a matching certified algorithm is an algorithm that just always outputs a matching, but maybe not necessarily a maximal one. And the key idea here is that we're going to grade matching certified algorithms by a metric. So specifically, we're going to assess algorithms by their vertex survival probability. So specifically, in a deregular tree, consider a vertex. All vertices are the same in a infinite deregular tree because they all have the same view. So pick a vertex and pick IDs for all of the edges in the neighborhood of the vertex. And ask, like, what's the vertex survival probability is just the probability that the algorithm does not match that vertex. And for example, Luby's algorithm, roughly speaking, it has intuitively it has vertex survival probability roughly to the minus R, or like a constant to the minus R, so exponentially low in R. And sort of a natural question is it the case that any matching certified algorithm has greater than exponentially decaying vertex survival probability? And the answer is yes. And this is the key technical result. So specifically, we'll show that. So the main theorem is that any R round matching certified algorithm has vertex survival probability at least C the minus R. And we're going to show that via a round elimination lemma, which shows that an R round algorithm for matching can be transformed into an R-1 round algorithm with a constant factor higher vertex survival probability. And once you do this, the main result follows pretty immediately because you get a 0 round algorithm or it's sort of similar to the existing round elimination framework. Okay, so then what do you do with this theorem? This is sort of one slight point of departure from the standard round elimination framework as well. And basically, we're going to do a global step here where we show, let's assume for the sake of contradiction that we have a fast algorithm for maximal matching. Let's, by the key theorem, it has high vertex survival probability. So it has much higher than 1 over delta vertex survival probability. But that means that a bunch of vertices have to survive. And in particular, the set of surviving vertices is bigger than any independent set in our graph, in our hard instance. So therefore, there must be 2 vertices that are adjacent, meaning that the surviving vertices that are adjacent, meaning that the matching that the algorithm produced is actually not maximal, a contradiction. So that's sort of the sketch of the argument. And sort of the main meat of the result is improving the key theorem. It's worth noting that the simplified paper that followed ours also proceeds by this sketch, but they have a simpler proof of the key theorem. Okay, so conclusion, matching on regular trees requires at least the minimum of log d and square root log n rounds. This has many implications. And in particular, we got a lot of interesting separations. Matching, in particular, MIS and matching switch on trees, and MIS on trees is strictly easier than MIS on general graphs. This is proven via like an improvement to the round elimination framework, and there were several key ideas, specifically this vertex survival probability metric. And this, as we've already seen, this has already been extended to other problems, and I'm looking forward to seeing what problems happen next. Thank you.